Hi, welcome. Right, stuff's working. Cool. So, let's do some assembly, right? Right, so the first thing you gotta know is assembly is nothing like Java. Java is like you're doing some logic, you're figuring out some stuff, and it's just doing some logic. Assembly, however, is just playing with the hardware. We're playing ball with the hardware. So, of course, we gotta think completely differently when writing assembly, in opposed to Java. We can't just write if statements and all that kind of stuff. So we gotta work with registers and memory and all that fun stuff. So first of all, I'm gonna show off some really useful links that you probably want to see, and it is this one, for example, the x64 cheat sheet. There's a lot of stuff in here that you want to look through. You can see all the stuff you gotta need for this assembly stuff. And we're gonna look at one thing in the beginning I want to mention real quick, and it is calling conventions. This is really important. If you remember this, it's gonna save you a lot. All right. Secondly, we're gonna just Google something real quick. That is the C standard library documentation. Very useful indeed. Let it load. All right, so How's the resolution? Can you read the stuff that's on the screen? Okay, cool. So here we have a lot of stuff, all right? This is the C standard library. In assembly, we can use C standard library stuff. So, for example, we want to call a function. We can call a function from the C standard library like print. So that's in the input output section. So we're just going to go to the input and output section. So we can just search for printf. And there should be some printf stuff somewhere. Here we go, I think. I mean, this is like 1,000 pages, so printf. It's gonna be printf. All right, so here should be the reference thing, hopefully. Oh yeah, cool. Maybe that's not what I'm looking for. Preparation, guys, that's all. No preparation. Anyway, you just want to find some reference to the function you're looking for, like this. Yeah, there we go. So we can see the C code for printf, and it has a const char format and whatever variables here. So printf basically needs a format and your inputs as parameters. And in assembly, we can't just say call printf with these parameters. We have to put those parameters either in a register or on a stack. And here is where we're going to look in the cheat sheet and see the calling convention. All right, the calling convention as calling a function. And to call a function, a program should place the first 6 integer or pointer parameters in the registers %RDI, %RSI, RDX, RCX, R8, and R9. This is very important stuff, all right? So you want to remember this very well, all right? If you remember this, you got about 50% of your stuff. Cool. So here you can see an example. We call foo, and this is the C code, for example, or pseudocode or whatever. We can see that we move 1 into RDI, the first register, and we move F15 in RSI, so that's the second parameter. And then we call the function as such. So how can we apply that in our code? So let's go to our Linux, and we're going to look in our computer organization stuff. So let me grab my Brightspace and see what's the thing we got to do. Yeah, let me look. No, that's not the one. It's also nice. All right, I just gotta go to Brightspace. Yes, no problem. Yeah, your links get deleted, but that's okay. All right. So now I'm bright space, and you can't see that because I'm in the different stuff. But let me get the thing. The thing. Where's the thing? Lab. All right, there you go. Lab manual. So the first assignment, we're not gonna give you code for the first assignment, but we're gonna work you towards getting that assignment finished. So the exercise is to create a new text file called hello s, implement a simple main routine that exits the program immediately with the proper exit code and without crashing. Build your program and run it, alter your main routine, blah, blah, blah. So that's the first assignment. That's cool. So let's first talk about, let's see what's on the schedule, basics. So every assembly program has a text section. If you declare it or not, it has a text section, right? Just declare it explicitly like this, so you know it's the text section. We also have the .bss section. We have the .data section, and data contains variables that are declared. This contains variables that are not declared, and this constants. All right. Also, in assembly, we don't have the difference between capitalized and non-capitalized letters, so that makes things easy. We can also write this. It's perfectly fine. All right, don't define .text twice, and I always put my constants on the bottom because your code is also going to be where the constants are. Constants, you just define variables by type something, colon, and that's your variable name. And then you have your type, and we want an ASCII thing that is zero terminated because that's what the set is for. We have, for example, hello. Cool. So let's give it a proper name. Let's call this thing hello. Hello text. All right, I define my constants as all capitalized. That's very important. Someone asks if you have to have 3 sections in your code. No, you can just have one. It's also fine if you don't need your data or undeclared variables. That's fine. You can just have the text section. Sublime text, I just got it from the internet, and I have shh, don't tell anyone. It's very secret. You just Google licenses for Sublime Text and you get it. All right. Anyway, this is an ASCII zero terminated. All right. So if we don't zero terminate it like so, and we try to print this, it will print all the memory that's below it. Like there's some garbage memory below that. We're just gonna read through that la 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 until we hit a zero termination character and then it stops. So in this case, if you print this, we're in a little bit of trouble because it doesn't know where our string ends, and you can just do that to signify the same as what you said is actually for. This actually puts it in there automatically, but you can better use this. Other types would be word. All right, it's what they told us is 8-bit, I believe. And also don't declare two same things. All right, word. Lol. And we have, for example, quad, blah, I don't care. And you want to align these a little bit so it's easier to read, make your code a little bit amazing to read. So a word is 8-bit, I believe, so let's do something fun. That's a beautiful word. I believe we also have byte, if I'm correct at that. And that is just 1 byte, so it's in hexadecimal. So we know in hexadecimal 0x4 is actually So we comment with a hashtag 0000110. So this is actually one. Oh wait, this is I said bits, but I mean 4. It's basically that. All right. This is a byte. A word would be the following. We would have the following. All right. So this is the F, and this is the 4. And of course, because it's a word, it's a little bit bigger, I believe. So this is, and this is actually a nibble. Do we have nibbles in this thing? No, I don't think you can't really declare any memory that's smaller than a byte. Um, so this is actually a byte, so we can actually just do this 04, I believe. And a word is something like how big is a word? So we have a word, that's 2 bytes. So a word is actually something like that. And I'm gonna do the binary for that. That is 0010001110. So you can actually read these like so to make it a little bit more understandable. And so we're also gonna mix in some number stuff. And we also have a quad, which is basically 4 words. So we can also just put that between brackets. This is 1 byte, 2 bytes. This is a quad. It's like, I believe you can just declare a number. I don't know. But this will be converted to a hexadecimal number, to a binary number, and it will be actually padded with 0. So it's actually the size of a quad, which is 4 bytes, and I'm not going to write it because I'm running out of space. And I believe we also have D word, right? Double word. Maybe we're not using bytes. Maybe we use the D word. Okay. Do we have a quad word, D word? Yeah. Anyway, these are the most important types for now. We'll look at other types later. Let's go to the cheat sheet and see what data types we have. So let's look at the data sheets, right? At the data types. Data types, maybe? And nothing? Maybe? Please? You can just Google it probably, like data types in assembly. And here we have another beautiful HTML type page. And you can see this is different type of assembly, so we're not gonna bother with that. So AT&T, please. Everything is Googleable, so you can just use whatever. Yeah, data types, AT&T, constants. Yeah, you have .byte, you have here's some other cool stuff you can use. Anyway, this is cool. So this is all your constants in the text area. So we're just gonna declare one constant, and it is my name. I'm just gonna do an example. I'm gonna put my name in here. we're going to define it as a string of characters. You can also use string. It's the same as .ascii is. It's exactly the same, like 100% the same. It's just a synonym. You can use whatever. I used ASCII so I can explain the difference between ASCII and ASCII. We're just gonna write string and we're gonna write my name. Cool. Yeah, now it's my stuff. Now it's my program. Cool. Here we can also define some data. So that's variables that are declared. So we can just do something like banana, and this is gonna be a byte, or we're just gonna use a quad because everything we're gonna do is just 64-bit, and we're just gonna write 42, or let's make it hex 42. So we're a little bit original, right? And at the BSS section, we can do the exact same. So we say, for example, lovely cow, right? And we're just saying that this is a string too, but we're not going to initialize it here. So later in our code, we can, for example, put some data in string. And here is a very important part. This is all memory. This is all initialized in memory. This is put somewhere at some memory location, and I am going to make a section right here that is just going to explain what the memory looks like. Don't actually put this in your programs because it's not going to do anything, but this is our section for memory and registers, so we can look at our program and step through it and see what happens. Cool. So in our memory we have lovely cow, so I'm just going to do this, and it might be put at some place in our memory, for example this, I don't know. And at that memory location we can just use the label. So this assembly makes it easy, so we can just call a label instead of the memory address, and this contains a string, so it has some empty area for you to work with. So this is lovely. So this is created on Heap, I believe. Then we have our data. So this might be Heap or whatever. Then we have the data section. We have a banana. Cool. And we have some other data, maybe over here. I don't care. It's just for examples. Oh yeah. Thank you. All right. So I wrote some stuff here. Cool. Yeah, I have to get used to switching my stuff. Might be a good idea. So here, as you can see, we have lovely cow is a string. It's just initialized on the stack and it has nothing in it. Just put that. I don't care. They have some space over there so you can grow your string, and otherwise it has to replace it if it's really annoying because strings can grow and whatever. But it just allocates some space on the heap so we can later access that stuff. Banana, we have a quad, so it's going to put this in memory, and that's done, and later we can change that, so that's cool to know. Also we have .text, and his is actually a constant section. This is I don't know where, I really don't care. And we just have our string with our zero termination character. All right, so actually this is converted into numbers, so it might look like something like this or whatever. So it's something like that I don't, and then it ends with 0. This is actually not the translation of that, but this is how it looks in memory, and it starts over here, and it's actually going to grow, so it's actually going to consist out of multiple places in memory. So let's make this 56. This should actually be a multiple of 8, I believe, but 56, 48, or shall we just call this in bytes? Let's just call this in bytes. So this is the 50th byte, and then like the 52nd byte. And so first off we have that, and then we have that, etc., etc. And this is actually split up into multiple stuff, like so. And this is how it's represented in our memory. roughly. All right, roughly. Cool. So our string over here is actually put in bytes, and it's gonna grow. The heap is growing down, so it's gonna increase the numbers, I believe. And the stack grows up, so the numbers decrease. So this is our memory. This is like the heap. I'm just gonna put heap, heap, hurrah. Okay, cool. And then we have a section of our stack, or a section of our memory. What does make most sense? I don't know which one is above which. Let me let me look that up so we don't get confused. Heap and stack. So I can actually draw a picture of the heap and the stack. Cool, this is beautiful. This is absolutely beautiful. Yeah, boy. Yeah, all right, cool. So there's your stack, there's your heap, and the stack grows down. So I believe 0 is over there, and F, 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 my life is over here, and the stack grows down to 0, and the heap grows up to FFFF, my life. And here is some free memory. We can do whatever there. And here is actually the static data. So the stuff that I declared over yonder, yeah, the constants like this is actually somewhere closer to 0, probably. Like, I don't know, something like that. Let's just prepend these all with 0 so we know it's lower. All right. And above that we have the stack. All right. We have the stack, and there's some stacky stuff. The stack is actually also just part of memory, but it is a piece of memory that we know exactly where everything is. We have a base pointer. We have a beautiful base pointer pointing. Let's do it like so, pointing to some address OXFFFFFF343 whatever. Be a little bit original again, and it's pointing to some value in memory, and that's the start of our program. All right, and then we have a stack pointer somewhere else, maybe over like yonder, and it's pointing to wherever we are in the program right now. So we might have some other data over here. I don't care. So something like that. I don't care. It's just for visualization. We have the base pointer at the start of our program and the stack pointer somewhere in our program, and this one moves up when we push something on the stack, and it moves down, or up to here when we pop something off the stack. So here comes some assembly code to represent that. So we have some stuff over here. We have some cool stuff. Let's delete that. We're just going to use some constants. We're going to use that. Every program in your assembly needs a main. Cool. We have a main. All right, cool. We just call it main like so. Just declare it like variables or whatever. It's a label. So labels, there's no distinction between that and that, except we define this to be variable over here with this stuff. And here we can just define main as a program by just writing some instructions. And there is no difference in instructions or memory. It's just the same stuff. All right. The computer doesn't know that these are instructions until you tell it there are instructions. So we can just write a beautiful instruction here called pop, and we can pop something off the stack. We have push. That's to push something on the stack. And we can append a queue or a W or what or something like that, not an E or an R or whatever. But if you Google it, you can see that there is some. You can look in the cheat sheet and you can see which letters you can prepend or append. Yeah, append a D, a W, or a B, or a Q, and basically that determines how much you're going to pop off the stack. So maybe you want to pop a whole thing of the stack and it will pop an entire 8 bits or 64 bits. So 1, 2, 3, 4, 5, 6, 7, 8. That's 1 byte, 2 bytes, 3 bytes, 4 bytes, 5, 6, 7, 8. So it might write this, and you can, for bonus, if anyone can convert this number to binary, just pop it into chat for fun. Pop it into chat. And so it will actually pop it from the stack. It will look at the stack pointer and see, oh, 49 is on the stack. So it's not actually this number, but we're going to pop 49 of the stack and put it in a register. We're going to put it in, call a funny register, RBX, whatever. All right, we're just going to pop it into RBX. And what happens is in the register section, like this is just to represent the registers, it's not actually code. We have a register. Let's do them in order. So RDI, which is the destination index. We have the RSI, which is the source index. So destination index, source index, and we have, looking at our cheat sheet, going to the calling functions, calling functions. Yeah, there we go. Or let's just copy that. Cool. So we have the data register. So that's what they are called. It's not necessarily what it's used for. And this is the counter. That's what the C stands for. And I don't make this stuff up. It's actually on Google. Just Google it. And we have just a temporary register. So let's call this temp8. R8. Cool. And this is according to the calling conventions. This is actually what every programmer should do when they are implementing libraries or whatever. And so RDI, RSI, RDX, whatever, these are registers, not memory. These are not found in your RAM. These are found near the CPU in little memory sections called registers, and this signifies it's 64-bit. You can also use the EDI version or the DI version even, I believe. Like just use DX, or no, it's like DA. Again, just look in the cheat sheet. I will put that stuff in the WhatsApp group so you can see whatever cheat sheet it is. And so you have like RAX, EAX, AX, or AL. And let's go back to Paint so we can see what it looks like. Let's grab a picture of internet again. Assembly registers 64-bit. And yeah, beautiful. Oh no, security error. Cool. Let's grab this other one. Cool. All right. Yeah. This is everything. Everything I'll need to explain. So we have general purposes registers. So we have our RDI, our RSI. You can see this is 64-bit. 64 bits. So this is 0th bit. This is the 63rd bit. And we use RDI, and if we only want to use 32, we can just use that section. We use EDI for that. All right. And if we want to use even less, we can use that part of it, only 16 bits, and then we use just bx, right? Yeah, we just use the last two letters. We just scrub the E again, just get SI. And if we want to go even further and only use 8-bit, we can just use AL. All right. This stuff was all explained in the lecture, so I'm just gonna finish off all the stuff here. You have floating point registers or zwevende kommagetal registers. Yeah, cool stuff. With the instruction pointer, you usually don't want to mess with that unless you want to break your program, like destroy it, like unless you're an expert, like just don't touch RIP. Like you literally rip your program, like because you're just the instruction pointer is pointing to your instruction, like move something something, and you just put this somewhere else in memory, and there's like kill computer, and it just destroys everything. You know, you don't want to mess with that unless you know what you're doing. Your program, so you know what you're doing. So RIP, rip. And we have some SSE registers, which I don't fucking know. Okay, cool. So let's go to Linux. Let's go back in here. And as we can see, we pointed RBP at some random memory address. So what is an RBP, you're asking? It's actually this value. So let's call this RBP base pointer. RBP contains that stuff, all right? Let's prepend OX to signify it's hexadecimal. And we have our stack pointer. And this is actually RSP. I'm so dead. Like, I'm getting my fever or whatever. I'm like, dying. Anyway, let's do the instruction pointer too, so we can destroy our computer and stuff. Let's do that. RIP. And this is actually pointing to our program. So let's just put that stuff in heap, I guess, or in constant section. It's actually in the constant section. Constant. Let's be a little bit thorough with our stuff. We have a constant section. You don't have to write this again. This is just, I don't know if there's new people joining, but this is just to explain you guys. And we have our program, like, let's just use shorthands, that like 20. I can't, well, yeah, hate you. And OX 21, OX 22, OX 23, and you write your code over here, right? So we have popq, and let's remove that again. Popq rbx. This actually, behind the scenes, this consists out of two operations. First, you move some data from wherever our RSP is. So we'll remove whatever is at RSP. And at the memory address of RSP, because RSP contains this, cool? It contains that. So we look at the RSP and we say the memory address. Okay, we gotta look inside that memory address and find 49. If we were to write this, however, we will get the memory address, and that's all kinds of garbage. We don't know what it's gonna do, and it's gonna destroy our lives and rip, you know. And second of all, you want your destination. So let's put that in RBX because that's what we defined over here. So that is over there, right? So it just moves our value in RBX, and then we just subtract, actually we add to the RSP. And what are we going to add to the RSP? We're going to add 8 bytes. because we're moving 8 the stack, right? So I think it's a 64-bit stack or whatever, so it just jumps. And what happens then is we just add 8 to the RSP. So let's make this multiples of 8 or whatever, so it's easier to understand. The other way around, please. Thank you. And so it's like at 32. It's at 32. And what happens is after we run this, it's going to put 22 into RBX, and it's going to move our stack pointer up. Or no, it's gonna copy 49 because that's where it usually where it were, and then it adds 8 to the thing, and it jumps up. It's gonna add 8 to the memory address, not the actual value, and then we get 22 in RBX. So let's make another one. Base RBX. Cool. Now that contains 49, right? And were we to do popq again in RBX, what will happen is we'll just copy 22 in RBX. We're just gonna overwrite that, and RSP is gonna add Q again, so it's now at the base pointer. And if your stack pointer gets above the base pointer, you are outside of your program. So if we were to pop Q again, we might have a different program here of the kernel or whatever. I don't know, whatever called this stuff, and they might have a beautiful number here like 42. And you're just gonna pop Q your base pointer. This stuff all just disappears already because you're beyond your stack, beyond your stack frame and whatever. You're just gonna pop 49 off, and what will happen is you're like outside of your program. So you're gonna do some malicious stuff to outside of your program, and you'll probably get a seg fault because you're not allowed to get to that memory, because the system knows this is where you started and that's where you're going to end. If you don't end there, you're doing malicious stuff. So just remember to never pop too much of your stack, because then you're going to do some weird stuff. All right, so let's start doing push. All right, cool. Push RBX. Now, hey, we're gonna push RBX on the stack. All right, so let's do this. Move Q RSP RBX. Well, it's gonna be a little bit different this time around, not like so. How do I move this? No. Dang it. Control Shift plus. No, maybe. Dang it. Struggles. I just cut it. Whatever. Cool. And now instead of adding, it now subs. Jesus, I just told you what it did. All right. Quickly about pop. Pop actually just, what it simply does is it adds, like it first moves whatever value the stack pointer is pointing to. It moves that value, not the memory address. It moves the value into the register you specified here. So if this is pop the register RBX, it's just gonna pop that value at RSP into that register you specified, and it moves the stack pointer up. All right, that's all it does. It copies the value at RSP, and then it moves the RSP up. So basically what happens, you can visualize that as let's delete everything. Cool. This is your beautiful stack. Let's actually make it a triangle, because then you can do Illuminati confirm and stuff. And we have some, this is like my beautiful pyramid RSP stuff. Cool. RSP is pointing to here. Your RBP is pointing to here. This is your stack. Struggles. Stacks. All right, this is stacks. So we have a beautiful value of 12, I don't know, 414, 42, 32, 42, like 42, like 42. Yeah, so we have our, this is the thing we want to pop. So we say pop q. Let's actually write that down. Pop q into rbx, right? Pop q rbx. Let's draw a couple registers here. This is beautiful paint, guys, like rbx. We have rbp and rsp. And in RBP, RBP we have like 0, 8, 16, 24, 32. We have the memory address, so this is mem address with memory address 32 and RSP 0. So we have RBX. We're gonna pop whatever is at RSP at memory address 0 RSP, and there is 12 in there, so RBX becomes 12, right? And we have our new value. So what happens then is the RSP is actually moved. It's going to be moved down to 8. And so now RSP is going to be pointing over there. So that's going to move there. And we have 12 here, messed up. And this is actually out of scope. It's gone. And now RSP is over there, so it's actually 8. Cool. We were to pop again, it will put 414, so we're going to do it again. Put 414 in there. RSP will be moved down and will contain now 16. Now, if we were going back here and we were to push Q RBX, it will actually subtract 8 and from RSP, from the stack pointer. So it moves the stack pointer first, and then it's going to take whatever you specify, send RBX, whatever you specify, and put that at where the stack pointer is. All right, so this is like the opposite, basically, of what we had before. And so what happens is, instead of push, let's just undo it, la la la, and let's just delete that. And we're gonna do push Q, and let's put the RSP down like here, whatever. And let's just say this is out of scope. This is our 12. We just did our pop. Yeah. Pop and push automatically change your RSP because they basically exist out of these two commands. This and that is exactly the same. All right, this is equivalent. You know what equivalence is, because RNL, you know, equivalency. They have the same truth table. They get the same output. And this is actually so these are equivalent. It's my, no, I'm in the wrong section. All right, now you can see what I'm doing. Yeah, sorry bruh. Pop ads. So if we push something on the stack, we first move the stack pointer down. All right, so if we push something, we first move it down. The RSP, we move that down. That's like embedded in this instruction. And then we copy whatever is it, RBX. Cool, 22. Oh no, we already had 49 here. Well, it's dead. It's officially dead. We moved it to RSP, right? And PopQ is basically the opposite. It first moves whatever is at RSP. Let's actually do it correctly. Yes. We first move that stuff, over to RBX, and then we add 8 to the stack pointer, and the stack pointer moves up again. And you can see that in our beautiful paint thing. We push Q, RBX, Q. So RBX might still have 12 from the last time, but when we push, what's going to happen is that 12 is going to die. We're just going to push whatever was in RBX. So we had 12 in our RBX, but let's say we had something else like 69. This will be overridden with, let's do some beautiful overriding. Blah. All right, blah. It's gone. It's gone. Now it's 69. 69. Illuminati confirmed it's on the top of the stack. Cool. Yeah. All right. Thank you. I'm a legend. No, I'm legend. I'm like, no. So now we have RSP at 69, and of course we gotta update this to 0 after it was 8. And that's basically what push does. All right, delete that stuff. Enough with the stacks and all that Illuminati stuff. Like, we're gonna get haunted. Did we screen swap? Yeah, we screen swap. So let's actually update this stuff. La di la di la properties. Yeah, just remove that. All right, cool. Oh, actually copied. Nice, 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 nice. All right, so we know what pop is and what push is, so this is the stuff, and it's all in main. But we have not discussed one very, very important thing, and if everyone is still here, this is like super important. Like, if you don't have this, your program will run. Global. All right, global, global, very important. Global, right? You got it. Global main. You put your label name here. You put your whatever label there. This refers to main. Main is now in the symbol table. Another term, another section I'm going to create here to explain. Symbol table. Yeah, boy. Like symbol table. Like, yeah. Cool. This contains all kinds of things like printf, scanf, exit, banana YOLO, water polo. Well, no, it doesn't actually contain that. Sorry. And some more C-lib stuff like C standard library, C standard library stuff. It's like all in there. It's defined and whatever it's loaded in, and it probably contains some other stuff, some other stuff. And what you do when we define this global main, what it actually does is some nifty stuff, and I just put your main in the global symbol table. So when we try to access it using our shell, so let's write a shell code thingy. Cool, this is now our shell. So let's another section, shell. All right, the shell. We're just gonna write our program name. What this does is actually just gonna call main, right? And it's gonna call main. It's gonna look through the symbol table and leave a, hey, we found main. Actually, it's not main, but this is like encoded to some other garbage, so we can't have two symbols be main. That's what assembly does for us, fortunately, so we don't have to write this ourselves. This is actually just some garbage, I don't care. So it's gonna find that stuff. It's gonna call main and see in main, oh, we are going to that program. It's gonna actually the prevent program name or whatever. I don't know what's the actual thing, because we can't have multiple mains like program name main or whatever. So, something like that. It will prevent something or append something, so we can't have two mains in here. And it finds main. That's what global does. do we want to define something else global? We can just do global banana derp. Alright, banana derp because it's derp and banana derp. And maybe banana derp is actually a string. And we want to define a global variable string. Define global variable in assembly. Okay, cool. Yeah, it's a little bit difficult to explain, so I'm just gonna go to this page, and you can see we have global test, and test is a label, and that's where your program starts. And you can also do this, and if we are like in our C code, or we're like writing some C code, we can just extern void test, and this is actually the test over here, so we can communicate with C code, and we can do some more weird stuff. So actually you can also write a C program, just call main, and we'll find main, and we find R14 save, and it will be a word R14 save, so extern and sign int, whatever, you know. You can do some very nifty stuff with that. So I'm not going to go too deep in that because it's beyond our scope. But if we define global bananderp, it will actually put that in the symbol table, and we have there's a bananderp, and we can also just call bananderp from some other program, and so we can actually make multiple program files and call functions from each other. And you should actually prevent these with some stuff so you don't get duplicates. But again, that's just some extra stuff, like whatever. So yeah, that is a little bit of symbol table stuff. That's what global does, and that's some questions. So your question is answered here by that's what global does. And this is why we define main as global, because your program needs an entry point. So we're just gonna write just our program, and we'll just actually do some call main stuff, you know, add your program, like from user, like some extra stuff, so it's not any other main. Kill that line. So that's what global does, and this is our label for main. That's where our program starts, and actually this is where I'm going to explain that your program is actually part of memory. So like we're just gonna write a very simple program. It's gonna push RBP. It's gonna push RBP on the stack. So what this does is it's gonna push RBP on the stack. Why do we want to do this, you ask? Well, actually every program has a stack frame. Let's call this the stack frame. So this is stack frame. Cool. This is our stack frame. And here, actually, I'm just gonna copy this stuff over. This is the stack, you know. The list is maybe like 56 and 64. This is not +8. 72. All right, cool. So we can't have duplicate RBP and RSP. So this is maybe some stuff like we have RBP of the previous program, and if you ask your question in the last like 5 minutes, ask it again, because I switched my Twitch chat, so but that's okay. So this is the program that calls our program. It has a base pointer at its start of its memory, all right? When we start the computer, it just starts somewhere, and the stack grows to some point. And then we have the kernel or whatever. That's the basic input-output system to the hardware or whatever, you know, roughly to put it in Otto's way. And it has an RBP. And if we try to call our RBP, we actually get that RBP, and we can do some weird shit, you know. But we want to push that RBP on the stack, so if we are done with our program, we can restore the RBP because we actually saved it on the stack, and we can just restore it for the other program that called us. So we're not, this is our fellow neighbor that said, hey, how you doing? How you doing, bro? Here, I have some stack stuff, all right? And if you don't save that RBP, the poor neighbor is gonna be like, what the hell did you do to my RBP? Where's my base? I don't know where my home is. I can't get home now. And that's why we are very sweet as the Callies. We call this the Callie, and um, whatever calls us, like call main, this guy is the caller, all right? And we have a caller convention, and we have a Callie convention. The Kali convention is that we push our fellow neighbor's color base pointer on the stack. So the first thing we actually do is we're actually just going to push RBP on the stack. And we do that by just saying, hey, RBP contains this. That's the memory address of our fellow neighbor. We just put that in RSP. Or we'll put that at the RSP, as we know what push does. It basically pushes something on the stack and moves the stack pointer. So now we have saved this stuff. So later when we pop it off the stack, or actually I did it wrong. The RSP was here, but it moved here and then it pasted it in. Remember that when you push it, it moves it first and then pastes it. And if you pop it, it first copies it and then moves it. All right. That's very important to know. Like push is move first, so push is move first, pop is copy first. All right. And now we have saved this under our RSP. So our RSP is actually pointing to this. All right. It's pointing to that. Our RBP is actually still that. So our RBP is basically the base pointer of the other program. So we still didn't move anything. We just saved it. All right. So when we're gonna return our program, we're gonna just put it back. So we're just gonna move the base pointer back to that address. But first off, we want to move Q our RSP RBP. What? What is this? So let's see. Move Q RSP RBP. Um, that doesn't work. That's why use brackets to say, oh, I see what you mean. RSP. Do I? No. I do it wrong again. No. If you do this, if you do this, it actually goes to the memory address and then it looks up and it sees RBP. So I believe this is actually correct. Is this correct? It should be correct. And if we look real quick, this is the lab manual. We actually, if you just read this thing, this is what I just explained. We have the stack. We have a stack that grows towards the heap, and heap grows towards the stack. And above the heap, we have our BSS section with undefined variables. This is actually in the heap. This is all heap still. So the undefined variables is at the bottom, data is there, and our constants is over there. This is like 0. This is f, my life. All right. And we have some stuff over there. Cool. All right, here we go. As you can see, this is actually the code to push the base pointer on the stack. And Then we move whatever is in RSP into RBP. And I'm losing my voice, so I'm just gonna get some water. Be right back. All right, guys. Ready? Ready to rumble again? You got your water up, Grados? So we left off at doing our calling convention stuff. Conventions are basically promises between programmers or whatever. To say, I am gonna promise to do the exact same as everyone else does. So everything is super easy. This is a convention to do the first argument, second argument, and so on. These are integer arguments. You have to use those weird floating point, zwevende komma, vliegende komma getal shit, and the rules stuff. You know, yeah, conventions. These are promises. So we just do RBP. We push RBP on the stack. We did that. Now we're gonna move whatever is in the stack pointer. So the actual memory address. It's always the memory address of RSP is always saved. It's always the memory address that RSP is pointing to is what's saved in RSP. And every time we move the stack pointer, it's basically just a register with some data. But you can basically overwrite this with whatever, but then you're gonna destroy your computer and stuff. It's pointing there. Cool. We are copying the address. All right, cool. We copied it, and where we're gonna put it? Oh, we're gonna put it in the RBP. Where's RBP? I'm a lazy ass computer. I'm just gonna follow instructions. Boom. Now RBP is pointing to the same as RSP. So now our base pointer is here, and we have no clue where our base pointer, the other program, is. And so what you do with every program is you return the base pointer to what it was, and you can see that in the lab manual how they do that with the movq rbp rsp and popq rbp. That's the epilogue. You have the prologue and the epilogue, and it's basically in every function call. In every function you do that stuff. Cool? Cool. All right. Now, what did we just read? We read movq like Russian. movq rbp. The rsp. Cool. Now what does this stuff do? We move this is our base pointer. Our stack pointer could be somewhere else in the program. We did some fun stuff and blah blah. We have like some dank memes on our stack. You know, we have like some dank memes on the stack. We did some weird stuff, and you don't want to talk about it. You're just gonna say, all right, we're just gonna reset our stack pointer to our base pointer, and then we're just gonna plop, pop, 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 pop our RPP. We're just gonna pop whatever is under RSP. We know what pop does. It's gonna read at the RSP the value, this, all right? And then it's moving that into RBP. And so we're just gonna paste that in RBP, and RBP is therefore gonna move over here back to where it was in the other program. So Stackframe of other program, make it more descriptive. The Kali, the legendary Kali color, we, the Kali. It's a run. Cool. So we have the legendary color. It has its base pointer back. Our neighbor is happy again, and we can exit our program. And it's just done with the program. In a subroutine, in a function call, we just use red to return, and I'll explain what it does exactly in a bit. But we're just going to call exit. This is actually in the symbol table, as I described it below. It's going to find exit. It's going to run exit. And what does exit do, you ask? Okay, what is call exit in Unix? And we're just gonna go over there, and it says blah blah blah, how it works, yada yada yada. Read that in your own time. It does some cleanup. It orphans some zombies. Ooh, zombies, cool. Assembly is cool, actually. It has zombies. It's super dank and stuff. No, but yeah, whatever. Basically it just cleans up your shit. So if you are doing some very dank stuff, it's just gonna clean up some mess. Even if your stack is a little bit rubbish, it's gonna finish that stuff. And well, is there anything here? Oh, here's your gas. Here's your gasoline. They do some other stuff. You can also do this, I believe. And I don't know if this works actually. Oh no, you have to probably use 64-bit stuff. You know, exit basically just handles the stuff. It cleans up some stuff, and you can read about it over here. So we usually just do call exit to just say like, hey, have fun with it. We did our stuff. You handle the shit now. And after call exit, it just ends our program. It goes back to the kernel. We're back in the legendary caller. All right. This is your boilerplate. This is actually all your program needs to contain. And this makes sure that the RBP moves to your start and back. Now we're just gonna have a subroutine real quick. So we have a beautiful subroutine subber. Alright, chat, give me a dang name for subroutine, right? Meanwhile, we're just gonna call it subber. Just give me a dang name. Give me a dang name. I mean, I already know one, but oh yeah, it might be a good. Thank you. All right, give me a name. Give me a dang name for the subroutine. Yeah, that's what I thought. So we have our Andy, and Andy subroutine. Cool. In our Andy subroutine, we have again the boilerplate stuff. I'm just gonna copy paste that stuff. All right, done. All right, we finish. All right, cool. Red. Yeah. Okay, this is your subroutine. This is what it's gonna contain. It's some boilerplate stuff. Let's even give you another life hack, and that is enter, enter, enter 00. Let's roughly translate this. I'll come back what red is. Red is basically return. But first we're just gonna make this boilerplate easier to read. We know what it does now. So this is roughly equivalent to this. All right. So we just use enter 00. And because this is a gas AT&T, we have to prepend those zeros so it knows it's numbers and not something else. And now we have that. We can still use this, but instead of doing all that stuff, leave. Done. We just wrote 2 lines instead of the 4 lines we had over here. Write this and you look like a pro. But write this and don't know what it means, and you'll probably be called fraud and you're gonna fail this course and everybody is gonna hate you for life, and Otto will probably say that you are not even gonna make it roughly with the carry bit, you know, like so just know what you're doing when using this. Basically does the exact same. Let's actually run this program. Actually, it should work. Let's save this in assembly yank tutorials. All right, so let's call this yank. Let's call this Andy. No. Andy is too over. Like, let's call this Otto. All right, give Otto some love. All right, can we have some love in chat for Otto and Andy, please? Can we get some love for Otto and Andy? Right, we gotta get some love, right? Yeah, boy. Right, Otto. So now we have a program, Otto. Here comes the compiling of our beautiful shitty program that does absolutely nothing but call Andy. Yeah, and we're just gonna compile that stuff. Let's cheat a little bit, and yeah, that's my password. No, I'm just kidding. This is your boilerplate stuff with no pi, so we're not gonna have some tasty stuff, all right? And it's called auto.s. Here we are calling the GCC compiler, so the GC compiler, and without PIE, which is process indeterminate encryption. I don't know what PIE stands for. No pi assembly. Oh dear. Oh dear. Oh dear. Oh dear. I tried to Google, but they don't like me. No, so no pi um, command. What is PIE assembly? GC no pi. All right, here. Position independent executable. It basically means that it's gonna put your program at some random place in memory, so it's difficult for people, for hackers and stuff to do malicious things with your program and stuff. So we turn that off, so debugging is easier, but hackers also have easier to debug our code, and we don't want that. So this is our stuff. As you can see, it doesn't work. Yeah, because I'm a failure. No, I'm just kidding. We actually have to go to documents, and then wherever it's located, I put in documents. So cd documents assembly yank tutorials. And actually that doesn't work because you have to not do the slash in the front. So now we are in dank tutorials, and now if you run that same command by using our up arrow to go there, we get a warning. End of filing comment, new line inserted. End of filing comment. Let's try it again. Well, it's nothing. It's just a warning, but we have an end of file in our we probably have some comment that is that we shouldn't really have. And let's just do that so it's not over there. Yeah. So our comments probably contain some characters. So let's just remove that just to be safe. All right. So now our code has no warnings, nothing. It made our file somewhere. If we go in the file system, we can see our you know, I didn't prepare this, but 1 second. Um, yeah, yeah. So all right, I'm back. So we just go to Documents, Assembly, and here you can see the output file. We have our source.s, that's this stuff, and the output file, and we can run this through the beautiful command line auto, and it ran. It did something. We don't know if it did something, so let's teach you a little thing that you can do with every program. That is, before you do anything, is you're just gonna add q $0, or no, move q $0 into rax, and let's see what this actually outputs. We can do echo that, and it's see is 1. Why is it 1? Why is it 1? You don't know. But if we do this and we have to compile it again and we run it again and now we echo that and it's 1, that means we probably made an error somewhere, right? Why would it be 1? I'm confused. So let's put it below leave. Maybe it needs to be below leave. Does anyone know what I'm doing wrong? Because I'm doing something wrong. I'm also just someone. I'm just a people. I'm a people. Um, let's look in the lab manual. Oh wait, I think I already know what the problem is, and it makes a lot of sense, and that is calling conventions. RDI, GCC, run it, and magic, it's 0. Let's put 10 in there, and again, gotta compile it, run it, echo it, and voila, 10. Magic, all right? Magic. This is basically our return value, and see if we have some unexpected behavior, we can just return -1, and we know that our program has exited wrongly, and we want to take note of that. But because it exited properly, we just put 0 in RDI, and we know RDI is by our calling convention the first argument of exit. And so exit is actually going to take what is an RDI and sees, hey, it exited properly, it exited gracefully. Any negative number and knows it's an error, it's not going to do anything, but it's just for if we want to debug it, and we have a lot of exits, and some are buggy exits, like unexpected behavior, we want to exit a program before it does something weird. We know, hey, it did something weird, and we can just go to that exit code and know, oh, it stopped there for that reason, and we can debug it. Cool? Let's just teach you a real quick way to combine these. We can just pipe them. Just use the pipe symbol, the thing used for OR. We just use a single one. We just write our second command and echo $s, and voila, it just does all the 3 commands in order in one time. And we can easily change this, and it will just change. It should work. It should work. And it doesn't work. Why doesn't it work? I'm telling lies? Because that doesn't make sense. Because this, that, and that seems to work. All right, so like so maybe, and then do that. Yeah, all right, so maybe there's something with compile time or whatever. So yeah, you can't do those two at the same time, so at least you can echo at the same time, probably. Does that work? No. And the reason why that does not work is probably because it echoes the whole command. So unfortunately we can't pipe that, but it was worth a try, you know. Maybe you have to use and. That would make sense. That would make sense to use and. No. We're already destroying everything in the entire universe. Whatever. We just have to write GCC and then compile it, and then we have to. Why the heck is it now in verbose mode? I destroyed it. And we can just do echo, and we can see too. Why is it doing that now? Alright, now it doesn't. Cool. Alright, so basically that runs program, and this is our exit code. Let's turn it back to 0. And we can see that the program actually runs. So yay, we achieved something. And we can actually do this over here too, because RDI is not being changed. And you have to know that registers are volatile. They can just be accessed by any called function. So for example, we just want to do something like this. Just say like move q what shall we call this? 42. Yeah, does that get old? In RCX or RBX, RCX. We move 42 in RCX and we call some function, and maybe this function does something like, okay, we're just gonna do some funny stuff. We're just gonna add one to let's just add one to RCX. Why not? Because we're not color safe or whatever. And we're just gonna pipe RCX into RDI. Let's see what happens. The sec faults or whatever. Whoa, 43. I thought we were gonna get 42. Well, we moved 42 in RCX, right? We called some function and then we put RCX, which is 42, in RDI. Wait. Stupid ass Andy. Andy, you silly beast. You added 1 to my value. You son of a gun. And that's why you can't trust registers, and that's why you push things on the stack. So we push 1 on the stack. We push 42 on the stack. Cool. And now we pop Q into RDI, and can you guess what's going to happen? Even though it used RCX or whatever, it's going to be 42. Hey now. Hey, cool. So what happened here is we pushed 42 on the stack. We just move our stack pointer, put 42 in there, and we're calling this stuff. So what happens when you call, we save the next thing on the stack, and then the RSP is going to move down and do all kinds of weird stuff. We do our RCX, whatever, and we come back here, and then we call popq RDI. It's going to take 42, put in RDI, the first argument of call exit, and move the RSP back there. And we leave. We know what leave does. It pops the thing, puts the RPP back, and it then puts the RSP back, all that kind of nifty stuff, and then we call exit. And it cleans up our stuff. And if we made some mess, if we made a real mess, you know? Now we're just gonna decompile call. We're just gonna disassemble call even further. What is this actually mean? And we're also gonna decompile ret. Someone asked, what does ret do? It return, but what does it actually do? Under the hood, call is nothing more than a push queue of whatever this is. So wherever the next instruction is, we can't really represent that with our own stuff. So that's why we have call. But say this is at memory address OX69. All right, this is our memory address. So let's just put that in the back. So this is at OX69. What this does is just gonna push the address of OX69 on the stack. So it's just gonna put it on the stack. You know, stack pointer is gonna move that on stack, and then it does a jump. So this does a jump. It does a jump, an unconditional jump to Andy. This theoretically, if we could get the actual address of this, again, we can also use a label. We just call this RT, is a return label. We can just push QRT. That should work. That should work. Let's try. Let's just try that. All right. Let's see if I'm right or wrong, or if this is gonna explode our computer, or it's gonna work. It's gonna work. It worked. It worked, guys. I just did experiment and it worked. It's because it's exactly the same. All right. I'm smart. I'm like legend. Like, no, I'm just kidding. This is just basically the same as that. RT is going to the memory address of where this is pointing to. This is nothing more than just a memory address with a label, so we can remember what it is. We can just put anything here, but this will assemble down to some memory address. It's gonna lay out this stuff in memory for us. That's what the assembler does. It's just gonna lay out everything in memory for us, so we don't have to specify location. We don't have to do all the grunt work of finding a free spot in memory and writing our zeros and ones in there. Assembly does that for us. We can use simple labels to define this memory address. So later when we call main from wherever, it's just going to look up the memory address. And in binary, it will just be a memory address and the first instruction. And then it's just going to read. RIP is just going to point to the first instruction. RIP is basically just over here. RIP is just over here. It just does the first instruction and does the second instruction. RIP is going to go down our program until it hits an exit, and then it's going to jump to another program and it does stuff. This is memory. This is all memory. This is what I wanted to do here over here. This is just memory. Alright, memory. So it's going to be main, and main, this is going to be main, right? Just call this main. This is main. This is memory. Alright? I have said this a million times. It's memory. Enter instruction. I don't know what the enter instruction. Maybe this is F0. And then the next instruction, alright, it's gonna be push Q. So like 34, 3F. This is also gonna have some arguments or whatever. And pref, it's gonna push Q RBP, right? So it's gonna have a C3 or whatever. It's just the binary. This is our program. This is actually our program. Cool. This is just in memory. We can also interpret this as data, and then it's gonna do some funky stuff, but it's just memory. Again, it's just memory. Call Andy, push Q, memory address of this line, and then jump to Andy. So now it's on the stack, all right? Now, how we never popped the return address on the stack. We never popped it off and called it. We never jumped back to it. So ret, what does ret and link told us? All right, no, just kidding. Ret. We still have 21 viewers. That's nice. So return. It's going to return. It's gonna do that. It's just gonna do that. So it's gonna pop Q. It's gonna pop. I don't know where's it gonna pop. Where's it gonna pop to? Ret assembly equivalent instruction. Just gonna Google it because I'm also newbie. Okay, return address, but yeah, it's gonna move the return address. Okay, this does not need any free registers to simulate ret, but it needs 4 bytes of memory. Oh, I think I know how it works. Okay, cool. So it's probably just not even gonna pop. Well, it has to pop it off. It has to pop it off. I don't think it cannot not pop it off. But it has to pop it off, maybe into a registry or whatever. But maybe this is also just done over here. Let me see again. And let's just do it with the registry stuff because that's way easier. We're just gonna pop this into ECX. We have a free registry, which is gonna fuck up their day. We're just gonna jump to ECX. So we're just gonna pop whatever value we have on the stack. This is the last thing we left on the stack. RT, as you can see, x69. That's RT. We pop it off the stack. This moves up again. And now RCX contains this memory address. We jump to it and we know that's RT. And now we're voila on this line of code. And this should work. This should be exactly the same if we remove this, and this. Save it. Let's compile it. We operand type mismatch. Operand type mismatch. Why would this be an operand type mismatch? What? This doesn't work, right? That would make no sense. That would make no. See? Oh yeah, thank you. I was looking at a thing. Thank you. Okay, now we have a warning with an indirect jump without star. Indirect jump. Well, it's just a warning, whatever. We're not gonna fuck that. Run it. Look at the output, 42. Let's change it to be sure. Compile it with warnings, whatever, who cares. The idea is that it works, and that is basically how it works. And thank you very much, Upgrados, again, for the good comments you're leaving. You get kudos from me. But that's what red does, alright? That is what red does. And this is what call does. Let's actually put this stuff back. Alright, cool. We have fancy ass code over here, and we're doing some cool Andy stuff. We can also remove this label, we don't need it anymore. Clean up our code a little bit, and let's just comment our code. We want some good commenting, so we're just gonna do some good commenting. You want to just go out here and comment your code and see boilerplate. Basically reserve color base pointer, and init callee base pointer. That's what it does. And this one, tabs or spaces, it just pushes 42 on a stack. We know what it does. It's really not that important, but we just want to do what we want to do in our code is basically push 42 on a stack, and that's basically turn, like, save our magic number on stack. So instead of just saying it pushes 42 on the stack, you don't want to write that. Like, I can read your freaking program and know what the instruction does. We want to know the context. Oh, it's a magic number, and you were just gonna save it on the stack for a while. Okay, cool. Now we know what it does. Now we know what you mean. And we're just gonna call Andy. So we just wanna call Andy. You can just say call Andy. Don't call Andy. Andy probably has a lot of stuff in his schedule, and he's a very busy person. Like, don't call Andy, but call Andy. Go to the subroutine for a check. So we wanna see if a call doesn't destroy our magic num. That's what we do in this program, right? And let's just do it in not chronological order, and we're just gonna pop q RDI, and so we just set the return code. So we set the return code by popping this 42 into the R2 magic num, which should be unchanged. Magic Then we leave. So there's gonna be another boilerplate stuff. Boilerplate just means it's basically in every freaking program. And we just set the base pointer back to what it was for our fellow color, and reset our stack pointer to the end, to the top of its stack frame. And this line is getting pretty long. Yeah, cool. All right, so that's a good comment. We want to comment this, and we're just gonna call C standard lib exit to handle my dankness. Right, so that's cool. And we have our Andy program. This is, you can also comment your subroutines by saying it's space convention. Let's just call this don't tamper my magic num test. What you also can do is for calls and whatever, if you're using for example, the exit is going to use RDI. Instead of doing that, we can also just write something like exit, or like C exit or whatever. So you understand its exit is actually a function with one parameter RDI, and we know that it's going to be 42, the magic number. You can either write 42 in here, but that would mean it would always be 42, but we want to check if it's true, so I'm just going to do RDI, for example, exit with RDI. This is also fine commenting, so people know you're calling exit with RDI, and we put this stuff in RDI, and so we can easily read through our C-lib code. You can even prepend this with a C, and just do something like this in your coding, and like do a C for call Andy without arguments. All right, bye, upgrade us wherever you are. But I'm gonna finish this stream in like 20 minutes. Maybe I'll stream again tomorrow with some more stuff about printf and stuff. Maybe I'll handle that this episode. I don't know, whatever. You can just write it like that, and you can just do something like this, and you can just look through your thing and see, C is a call, and see, all right, we're just calling Andy, we're calling exit, so you can just skim through your program a little bit easier and just see what's happening. And then here we have boilerplate. Let's just copy this stuff. I'm just gonna preserve color base pointer, so main base pointer, and init and EPP, something like that. Just handle your comments so everybody understands what the hell you're doing. At least if they saw this stream, they will definitely notice that you used my C convention that I just made up. And you can also use an A for Andy if you so love that. I mean, whatever. And is there an ad? Is there an ad rolling right now? Whatever. I suddenly see that there's an ad rolling or whatever. But we add one to RCX, so test if color uses RCX. So we're just going to see if the color uses RCX. And if it uses RCX, we can see we can see that it incremented 1, so we just want to test that. Cool. And we call leave. This is boilerplate stuff. Getting really old right now. Okay. Yeah. Well, whatever. And then it returns, and we're just gonna say go back to main, or you can just do C return. Why are you being so dumb? There you go. You can just call C return, for example, in your comments. Just say, okay, return, return. All right. So that's pretty easy. And this is our beautiful program. All right. And then we have our tutorial stuff down there. You don't need that stuff, but it's good for explaining. And yeah, that concludes the start stuff. We're right over our time already, but that's fine. We're just gonna quickly do some printf stuff, and then we're gonna end it at 22:30. And system dot you know yeah. So quickly, printf is C standard symbol table stuff. Printf, oh hey, we found printf. Cool. Let's call printf instead of Andy. We're just gonna kill Andy. I am gonna kill Andy. Sorry, Andy. Hey, look, Sublime Text has code folding. That's nice. That is really nice. That is beautiful. Andy, bye, Andy. I think I think I just moved our dear Andy to RIP. This is our meme now. Yeah. Well, goodbye. You served well in our test. But this is going to be printf, and what we want to do is RDI and RSI, and we can also specify that we want this to be number format, so number format 9, like this. Number format, and we can say in our comments, this is our text we want to print, and finally we're getting there. We're finally getting there. And you can even just do this, right? Something like that. As long as you understand your code and why you're doing it, as long as it makes sense. Let's just remove this push queue. Okay. Pop queue RDI. Well, let's make this 0 into RDI. And let's also teach you a little optimization, and that is instead of moving the literal value 0 into RDI, it's better to use XOR and RDI, and this works exactly the same. And explain to me tomorrow whenever you see me again in the WhatsApp group, whatever, I don't care. Explain why this works, okay? If you already know the answer when I explained you, like in class or whatever, don't spoil it. But if you're new and you see this for the first time, explain to me tomorrow or whatever. Explain to me why this works, and you'll get some extra kudos. And that's just optimization. It's way faster and it works the same, so why not use it, right? Let's call printf. We need another string. We're just gonna call this format num, format digit, format d, and it's gonna be a string, and it's going to be %digit, %d. And now we're just gonna put %d in RDI. That's what we want to do. So we're just gonna off queue whatever is at the memory address of format D, and put that in RDI. Why? We know that color convention, first argument. I'm dying slowly. Like my voice is dying. Whatever. First argument in RDI, and it's going to be present E. All right, cool. Let's put in format. I can also just do that. Format percent D or format. Format number digit. Cool. Now we know what it does. We have beautiful commenting. It's gonna move. This time we're gonna move into RSI. We're gonna move my name in there. That's what we're doing. And this is gonna be the second argument. The second argument, and it's going to be my name. String. Yeah, you can just do like that. Yeah, beautiful. Now we call that, and it should work. No. Hey, it worked. There you go. It works. And this is where I'm gonna end. No, I'm just kidding. See what I did wrong? See what I did wrong? Digit. My name is definitely a digit. Like I am a number. I'm definitely a number. Who's S for string? I'm just gonna comment here SD for numbers and S for text. And that's all you gotta know for now. There's other types like %C for charters or whatever. But we're gonna use S. And now we're just gonna run it again. And we see it's still not gonna do whatever we wanna do. But it's Melvin, student at government. Hey, it printed our name. That's nice. That is so nice. But we don't want this rubbish back. So a simple fix /n. And you know what a /n actually stands for? Is new line. And because n, like you can probably append n also, like so. No. Maybe like so. Maybe. No, maybe like so. Maybe. No. Is that NASM stuff? Well, you just gotta know that this is escaping. The n is basically to escape from our string. So this is not interpreted as text. So it's not written like so. Let's see what this does real quick. As you can see, it now puts /n after our text. That's what we expect when we write this. We'd expect this to happen. But because a backslash is a special escape character, it will escape the next character or next characters depending on what is behind it. In this case, it's an N for new line. You can also use a T for a tab. You can see that works. If we do this and that, it puts a little tab in here. I believe it also works for S or whatever, and it also works for 0, and that's the null termination character. We're just gonna do some funky stuff. We're gonna make ASCII. You know that ASCII already has the /0 at the end. ASCII doesn't. So you just write this. It just does the same thing as we expect with string. You remove that, and now we don't know if it's gonna crash or whatever. It might crash. Oh, it doesn't, and that is because the next thing it writes this in memory first, then it writes this in memory because this is 0 terminated because this has a 0 behind it. We actually don't die, but actually %s, the next thing in memory, is printed. In memory, this is actually just behind here, like so. It's like this is what's actually in memory. This is what's in memory. And then it's gonna print until it gets to 0, and it's like, all right, we're gonna print. Oh, we hit a 0, or just print this. And if we had ASCIIs or just string, it actually puts a /0 behind there. And now it will print and say, oh, 0, stop here. This is the next thing in memory, and we can see that's over here. So that is what /0 does, and that /0 is actually escape character for the null termination character. And n is for new line. And if we do this, we can see that it does print our stuff here and then inserts a new line. We can do it as many times as we want. And as you can see, it's going to put a lot of new lines, a lot of blank space. And if we really want to do something like a clear function, we just want to clear the chat, that might not even be enough. So let's do it even more. Now it's going to be a clear chat function. Boom. Cleared. All right. Pretty fancy, huh? And that is where I am going to end off our stream for tonight, because my voice is dying. I am dying. Everyone is dying. And this global main, yeah, it's just sitting there. It's fun. I'll just find some format that I like. And that is basically it for printf. This is how you can finish your assignment. So I hope you liked it. I hope you understand it. If there's any questions, if anyone watching still has any questions, either put them in the WhatsApp group or put them in stream. I'll answer them now. So we can just all right. Wait. Right. Okay. Now you can ask your questions, and if there is any within the next 5 minutes, I'll answer them. And otherwise, I'll see you in the WhatsApp group for any more questions. And if I have to re-explain something a little bit better, I did my best, guys. And I also enjoyed this stream. Maybe we'll do something like this again. Leave me suggestions or whatever, things I can improve on. But yeah, I hope you'll make it before Monday when you have to hand it in. I can also just for next time, like, save my notes somewhere. I can just copy these into the WhatsApp group for you, and I'll do that right now. So you'll pop it in right there, and you'll see my code. It will be in a paste bin, so it's not going to clutter your entire thing. Notes assembly x64. It's going to be unlisted. It's never going to expire. Gas assembly. I hope this works. Yeah, that's decent syntax highlighting, I guess. So I'm just gonna put the paste bin into WhatsApp, and that's the notes of our stream. For the explanation, you can go to twitch.tv/H&M124, I believe, and videos. That should be previous streams. Yeah. Find back our previous streams. There you go, and that's it for this stream. I hope you enjoyed it. I hope you understand a little bit better right now. And again, if there's any questions, go to the WhatsApp group, go to wherever. I'll be there to answer questions. Thanks for watching, and I'll see you another time.